Assalamu alaikum everyone. Today we have to start this topic which is about the parallel flow over the flat plates. So we have to consider the flat plates and how we can actually find out the thickness of the boundary layer over this flat plate. Okay, so there are some of the terminologies that we will use in this lecture. Let's see what we have here. First one is the velocity boundary layer. What is this layer? The region of flow over or above the plate bounded by a thickness delta in which the effects of viscous shearing forces caused by the fluid viscosity are felt. Okay, so what is the velocity boundary layer? This is this layer on this figure. So this is a layer on which you can have the effects of the viscous shearing forces. So you can see that the fluid enters on this flat plate, and as it moves along the flat plate, you see that there is an increase in the thickness of the boundary layer. Now, as the thickness increases, we can denote that thickness with the delta here, and we will see that how actually this boundary layer thickness is being developed and why it is rising as we are moving along the length of the plate. Okay, so let's see, we have here the boundary layer thickness delta is typically defined as the distance y from the surface at which u will become equal to 0.99 of the v. Now here the v represent you the velocity of the fluid, which is called as the free stream velocity. So what is the free stream velocity? We discussed earlier. This is the maximum velocity of the fluid that is away from the surface of the object. Okay, so as it is away from the surface of the object, what we can imagine that the fluid will be having a maximum velocity and there will be no slip condition. Okay, so as we move away from the flat plate, we will be reaching a maximum velocity of the fluid, which is called as the free stream velocity. Now what is this u here? U represents you the velocity of the fluid layer when it becomes 99% of the free stream velocity. For example, at this point we see that the velocity profile is being developed, but at this region the velocity of this layer, it will be approximately 99% of this free stream velocity. Okay, so as we are moving along this flat plate, we see that there is a rise in the thickness of the fluid layer, or that is called as the boundary layer thickness. Okay, so the hypothetical curve of u, that is equal to 0.99v, divides the flow into two regions. So this layer, it divides the flow into two regions, one that is below this line and the other one that is above this line. The one that is below this line, it is called as the boundary layer region. So this region, it is called as the boundary layer region. What we have in this region, the viscous effects and the velocity changes are significant. Now in this region, what we see here, that there is a viscosity, and you can see that there is a change in the velocity. So the layer of the fluid that is close to the surface of this flat plate, it will be having the maximum value for the friction and the maximum value for the viscosity, and it will be having minimum value for the velocity. But as we are moving away from this flat plate, from the surface, what we see that the viscosity will decrease and there will be a slight increase in the velocity of the fluid over this plate. Okay, so we can have this kind of velocity profile in this region. The other one, irrotational flow region. So this is the region that is above this boundary layer. We can call this one as an irrotational flow region. The frictional effects are negligible and the velocity remains essentially constant. So above this region, we can have a very less variation in the velocity and the viscosity, and the fluid velocity, it remains essentially constant. Okay, now let us see what we have in this figure actually. Now let us see that how we can actually make this boundary layer thickness over the flat plate. Okay, so for this thing you have to see the boundary layer thickness concept also, and you have to see what is this one, free stream velocity. So if I show you this figure here, now this is the similar figure that I show you in the previous slide. So what we have here, if you look at this red line, if you look at this red line, it represents you the boundary layer thickness. Okay, at this particular point of the velocity profile, the velocity of this layer will become equal to 99% of the free stream velocity. But as the fluid is moving forward, more of the fluid is coming into contact with this flat plate. So what we see here, the velocity value that we get at this position earlier, now this position will be slightly increased. Okay, so we have to move away from the flat plate. Why? Because the frictional force between the fluid and the plate, it will increase as most of the fluid will come into contact with the with this layer of the flat plate. Okay, so to get the same value for the velocity that we get here, now at this particular position we have to go slightly upward. Okay, so at this point we can have the velocity boundary layer or the boundary layer thickness, and for the same value for the velocity, now the boundary layer thickness has been increased. But now what we see here, as we are moving along the length of this plate in the right hand side direction, the more of the fluid will be coming into contact with the flat plate, and this value for the maximum velocity or the thickness of the boundary layer, it will keep on increasing. Okay, now the first part here, coming back to this figure again here, now the length of the flat layer, that is starting from the leading edge of the plate to the point where we can have the separation between the laminar flow and the transitional flow or the turbulent flow. We can call this length to be the critical length. Now how we can actually find out the value for this critical length, I will explain you later in this lecture. But for now, what we can see here, there could be three boundary layer formation within this flat plate. First one, it is relevant with the laminar flow, then we can have the transitional flow, and then we can have the turbulent boundary layer. Now in the turbulent boundary layer, what we see here, there are 3 to 4 sub layers here. So the layer that is very much closer to the surface of this flat plate, this is called as the viscous sublayer. So in this layer you can have the maximum value for the viscosity and maximum friction, and there will be a very low value for the velocity. Then the next layer, it is called as the buffer layer. So in this buffer layer, the viscosity, it is slightly less than the viscous sublayer, and the velocity, it will be slightly higher than the viscous sublayer. Okay, and similarly if we move upward, the overlap layer, in this layer you can see this one, there will be slightly motion of the fluid particles or the fluid layers. Okay, so what is happening here, in the overlap layer, the viscosity of the fluid will be even lesser than the buffer layer and the viscous sublayer, and you can see some zigzag motion of the fluid layers. Okay, so this layer is called as the overlap layer. Then we can have the turbulent layer, in which you can see that the fluid layers, they are mixing with each other and the velocity is changing. So this layer is called as a turbulent layer. Now again this one, the turbulent boundary layer can be considered to consist of 4 regions characterized by the distance from the wall. Okay, so the layer that is in contact with the layer of the flat plate, that layer is called as the viscous sublayer. The next layer is the buffer layer, and the next layer is the overlap, and the last one is the turbulent layer. Okay, now here you can see the concept of the free stream velocity also, and how we can actually get the value for the boundary layer thickness. Okay, so we represent you here the free stream velocity of the fluid. So when the fluid is coming into contact with the flat plate, there will be formation of the velocity profile. So this thickness here represent you the velocity of a layer of the fluid, at which the velocity of this fluid will become 99% of the free stream velocity. Then the thickness here, it is called as the boundary layer thickness. Okay, so there are some equations that we can use to estimate what is the thickness of the boundary layer. We will see that one. Okay, now here we are just considering the flat plate. We are only dealing with a flat plate here. So which equation we can use to estimate the drag coefficient? There could be two drag coefficients due to the frictional forces, and the drag coefficients due to the pressure forces. Now here in this particular example, the fluid that is coming into contact with the surface of this flat plate, it will be experiencing the drag force due to the friction drag only. There should be no value for the drag force for the pressure forces. Okay, so only the drag coefficient due to the friction forces will be considered in this example, that is represented by CF, and the drag force, it will be only a function of the drag coefficient due to the friction forces. Okay, and the rest of the equation is same. Now for the flat plate, what we have here, there should be no drag coefficient due to the pressure forces, and there will be only the drag coefficient due to the friction forces. There should be no value for the drag force due to the pressure forces, and there should be only the drag force due to the friction forces. Okay, so you can see these two equations here. So we have to consider the drag coefficient due to the friction forces, and then we have to consider the drag force due to the friction forces. Now let us see some of the more details here. The transition from laminar to turbulent flow depends on the surface geometry, surface roughness, upstream velocity, surface temperature, and the type of fluid, among other things, and is best characterized by the Reynolds number. So these are some of the factors that can convert the laminar flow into the turbulent flow, and that include the surface geometry, surface roughness, upstream velocity, surface tension, and the type of fluid. Okay, so all of these factors can be related with the Reynolds number. Now the Reynolds number that we calculated in the chapter number 8 for the flow in the pipelines, that has a different equation, and the value for the laminar flow and the turbulent flow was different, and then we calculated the Reynolds number in case of the packed bed, so the equation was slightly different there also. Now we have to calculate the Reynolds number for the flat plate. Okay, so there will be a slight change in the equation also here. So Reynolds number here, it will become equal to rho u x divided by mu. Rho represent you the density of the fluid, v represent you the upstream velocity, x represent you the characteristic length of the geometry. For the flat plate, it is the length of the plate in the flow direction. Okay, so x here in this particular Reynolds number, it represent you the length of the flat plate. Mu, it is the viscosity of the fluid. Okay, so we can have this equation, or in terms of the kinematic viscosity, we can slightly change this equation into this form. Now, what should be the value for the Reynolds number if we are dealing with the flat plates? Okay, so let's see the values for flow over smooth flat plate. Transition from laminar to turbulent region begins at Reynolds number approximately equal to 10 raised to the power 5, but does not become fully turbulent before the Reynolds number reaches the much higher values, typically around 3 into 10 raised to the power 6. Okay, so we can have this range here to differentiate between the type of flow, either it is a laminar or a turbulent flow. So if the value for the Reynolds number it is less than 10 raised to power 5, we can have the laminar flow, and if the value it is greater than 3 multiplied by 10 raised to power 6, we can have the turbulent flow. So these are the values for the Reynolds number when we are dealing with a flat plate. So it is not the condition like the chapter number 8 where we have the different values for the Reynolds number. Okay, so you have to just keep this thing in the mind. So in engineering analysis, a generally accepted value for the critical Reynolds number is, we can have this equation REXCR that represent you the critical Reynolds number. The equation is same as we see here, rho u xcr divided by mu, that is equal to 5 multiplied by 10 raised to power 5. Okay, now this value for the critical Reynolds number, it lies between the range that we see here. Okay, so the earlier range was 10 raised to power 5 to 3 multiplied by 10 raised to power 6, that represent you the transitional flow region. Okay, now for the critical Reynolds number value for the engineering analysis, the value for the critical Reynolds number it is fixed, that is 5 multiplied by 10 raised to power 5. Okay, now what is the use of this critical Reynolds number value? If you go back to this figure here, now what we see here, XCR, it represent you the region for the laminar flow. Okay, now you can estimate that what should be the length of the flat plate in which you can have the laminar boundary layer. Okay, so you can use this equation XCR, you can use this equation Reynolds number XCR rho ux divided by mu, and that is equal to 5 into 10 raised to power 5, and you can actually find out the critical length of the flat plate during which you can have the laminar flow, and after this length XCR, after this XCR you can have the transitional region and the turbulent region. Okay, so during this length of the critical this critical length of the flat plate you can have the laminar flow, and after this one you can have the transition and the turbulent flow. The actual value of the engineering critical Reynolds number for the flat plate may vary somewhat from 10 raised to the power 5 to 3 into 10 raised to the power 6, depending on the surface roughness, turbulence level, and the variation of pressure along the surface. Okay, so the actual value it can vary between these springs that we studied earlier, but for the engineering calculation we can rely on this value. So to get the critical Reynolds number value we have to rely on this equation, and to get the critical length during which we can have the laminar flow we can use this equation. After this critical length, what we have, we can have the transitional region and the turbulent region. Okay, so see, if we can have to just calculate the critical length for the laminar flow, or we have to calculate the critical length, not the critical length but the length for the flat plates. Okay, now let us see what is the friction coefficient. We have studied this equation earlier in this chapter also, but now let us see some of the more details in terms of boundary layer thickness. Okay, so here is the boundary layer, that is the boundary that is formed over this flat plate, and now we will see that CFX that represents the local friction coefficient and how it is changing in different types of flow. Okay, so the friction coefficient for laminar flow over flat plate can be determined theoretically by solving the conservation of mass and momentum equations numerically. Okay, so the value for the critical, the value for this coefficient of friction for the laminar flow, it can be calculated using some mass and the momentum equations. So I will show you that one. And for the turbulent flow, it must be determined experimentally and expressed by empirical correlation. So for the turbulent flow, we can get the value for the local friction coefficient and the overall friction coefficient using the empirical correlations. Now this CF, it represents you the friction coefficient of this entire plate when you are doing the integration on the length of this flat plate from 0 to the total length of this flat plate. So 0 to L represent you the total length of the flat plate, and if you do the integration on this local friction coefficient to get the value for the entire surface of this flat plate, then we can have the total value for the friction coefficient by using this equation. Okay, now this equation for the Reynolds number, it is simple, we have studied this one earlier. Now let's see here, if we are supposed to calculate the boundary layer thickness, if we are provided the Reynolds number in the laminar flow region. Okay, so what we can do here, what are the limits we have? First of all, we will check what is the value for the Reynolds number. If it is less than 5 multiplied by 10 raised to the power 5, we can have the laminar flow. If we are having the laminar flow, then we can use this equation to estimate the thickness of this boundary layer. Okay, so X represents you the length of this one flat plate. Reynolds number equation, we know this one. Okay, now this CFX, it represents you the local friction coefficient. For example, for this flat plate, you want to calculate what is the friction coefficient at this point, so you can use this equation directly. 0.664 divided by Reynolds number raised to power 1 by 2. Okay, so you will calculate the value for the Reynolds number, and then you will use this equation to get the value for the local friction coefficient. If we are supposed to calculate the total friction coefficient, we will show you some other equation. Okay, now if we want to calculate the boundary layer thickness in the turbulent flow region, then what should be the equation? That is equal to 0.38 x divided by Reynolds number raised to the power 5. Okay, and the local friction coefficient for the turbulent flow, it will be equal to 0.059 divided by Reynolds number power 1 by 5. Okay, so what you have to do here, you have to simply calculate the value for the Reynolds number. If it is lying within this range, then you are dealing with the turbulent flow. Okay, so once you are dealing with the turbulent flow, then the boundary layer thickness of the turbulent flow will be calculated by using this equation. Or if you want to calculate what is the local friction coefficient at this point of the flat plate, then you have to use this equation. Okay, so don't worry about these equations. These equations are usually provided to you in the exam. What you need to do here, you have to just calculate the value for the Reynolds number and see you are dealing with a laminar flow or you are dealing with a turbulent flow. Now these two equations, 1, 2, 3, 4 equations, these represent you the boundary layer thickness if we are dealing with the laminar flow or the turbulent flow, or the local friction coefficient at the points for the laminar flow and also for the turbulent flow. Now let's see if we want to calculate the total friction coefficient over the entire surface. Okay, now what are the new equations? Let's see this one. Now, average friction coefficient over the entire plate. Okay, so the earlier equations that we saw that were related to local friction coefficient. Now, these are the two equations that represent you the average friction coefficient over the entire plate. So, you have to calculate the value for the Reynolds number. Okay, if it is lying between the within the range for the laminar flow, then you can use this equation to estimate the value for the coefficient of friction for the entire plate. Okay, now these two equations are for the entire plate, not the local friction coefficient. Okay, now similarly, if the value for the Reynolds number lies within this range for the turbulent flow, you can use this equation directly to estimate the friction coefficient for the entire plate. Okay, so when we solve the numericals, what we are interested in, we are usually we need to calculate the value for the coefficient of friction for the entire plate. Okay, so we can rely on these equations, but you have to see the So if it is given to you categorically that you are dealing with the laminar flow, then you can use this equation to get the value for the coefficient of friction for the entire plate. And similarly, if it is provided to you categorically that you are dealing with a turbulent flow, you will check the Reynolds number value and then you will get the value for the coefficient of friction for the entire plate. Okay. Now sometimes what happens when the laminar flow region is not disregarded, sometimes we have to deal with such a situation that fluid is moving over this flat plate and now we have to estimate the value for the coefficient of friction. Now there could be two things. First region will be the laminar region and the next one will be the turbulent or the transitional region. Now we have to calculate the coefficient of friction for both the laminar flow and for the turbulent flow. So the new equation, it will have two parts. First one, local friction coefficient for the laminar flow and local friction coefficient for the turbulent flow. Now if you look at the limits here, if you want to estimate the total friction coefficient for the laminar flow, then you will do the integration from 0 to XCR, which is the critical length. That will represent you the local friction, that will represent you the friction coefficient for the laminar flow region. Now for the turbulent flow region, it will start from the critical length to the entire length of the flat plate. You will do this integration to get the total value for the coefficient of friction for the turbulent flow. Okay, or you can use this equation directly. You have to check the value for the Reynolds number. If it is lying within this range, then you can directly use this equation to get the value for the coefficient of friction for the entire surface. Okay, now what we can do here, we can see different equations here. Now which equation we can use actually? Now if it is given to you that you are only dealing with the laminar flow, then you can use this equation. If it is categorically given that you are dealing only with the turbulent flow, then you can use this equation. If no clear information is given to you that you are dealing with the laminar or the turbulent flow, then you will first calculate the value for this Reynolds number, and it is better to use this equation that incorporate both the part for the laminar and the turbulent flow. Okay, so this is the key. Now this is the derivation. For example, here we have the equation for the local friction coefficient, and then we do the integration over the entire length of this flat plate, and the value for the friction coefficient for the entire surface, it comes out to be 1.328 divided by Reynolds number power 1 by 2. So this is the same equation that we get here. Okay, so what we have done here, this is the equation for the local friction coefficient, and then we do the integration from 0 to L to get the value for the total friction coefficient. So the same thing we have done here. Okay, so we have put the values for the local friction coefficient, we have done the integration over the entire surface, and then the value for the total friction coefficient for the entire surface, it comes out to be 1.328 divided by Reynolds number L power 1 by 2. Okay, so this is the same equation that you can see here. Now let us see this one. For laminar flow, the friction coefficient depends only on the Reynolds number and the surface roughness has no effect. Okay, so if you are dealing with the laminar flow, then the friction coefficient only depends on the Reynolds number and surface roughness will be having no effect. However, in case for the turbulent flow, surface roughness causes the friction coefficient to increase several fold to the point that in the fully rough turbulent regime, the friction coefficient is a function of surface roughness alone and is independent of the Reynolds number. Now, if you are dealing, now these 2 points, these are quite similar to the things that we studied in the Moody's chart. Okay, so if you are dealing with the turbulent flow, then the friction factor will influence the total friction coefficient. Okay, and at a very high value for the Reynolds number or at a very high value for the surface roughness, then friction coefficient will only become a function of surface roughness irrespective of the Reynolds number. So for example, if you are dealing with a fully rough turbulent flow, if it is given to you in the question, if you are dealing with a fully rough turbulent flow, then you can use this equation to estimate the friction coefficient for the entire surface. Okay, now epsilon here, it represents the surface roughness, L represents the length of the plate in the flow direction, so it represents the characteristic length. Now this relationship, when you can use this relation can be used for the turbulent flow on rough surfaces. So the surface should be rough, the Reynolds number value should be greater than 10 raised to the power 6, and the surface roughness, it should be greater than 10 raised to the power minus 4. Okay, so you before applying this equation, first of all you have to see these conditions. So if you are getting the Reynolds number greater than this value and the relative roughness greater than this value, then you can use this equation to estimate the value for the friction coefficient in the range of fully rough turbulent flow. Okay. Now what we see here in this graph, as we are moving downward, what is happening? The surface roughness, it is increasing, or the relative roughness, it is increasing. Okay. So with the increase in the value for the relative roughness, there will be an increase in the value for the coefficient of friction. So you have to see different charts and you have to see different figures to get the value for the relative roughness and what should be the value for the friction coefficient. Okay. Now let us see this graph. This graph is quite similar to the Moody's chart. So let's see what we have here. Coefficient of friction increases several fold with the roughness in the turbulent flow. Okay, so this one is the turbulent flow. So if we are increasing the Reynolds number, what we see here, this green line, it is going upward. Okay, so what does it mean here? That the surface, if we are increasing the Reynolds number, then the coefficient of friction, it is increasing. Coefficient of friction is independent of the Reynolds number in the fully rough region. Now this is this dotted line represents the fully rough region, and after that region, what you see here, that the value for the coefficient of friction, it will become flat. Okay, so what does it mean here? In the fully rough turbulent flow regime, the coefficient of friction will not be a function of Reynolds number, it will become a function of relative roughness. Okay, so we see that if the roughness is increasing, the coefficient of friction, it is increasing. Okay, there is no change of the coefficient of friction with respect to the Reynolds number. The Reynolds number is increasing and the coefficient of friction, it will just become straight. What does it mean here? That the coefficient of friction will become a function of only the relative roughness. This chart is a flat plate analog of the Moody chart for the pipe. Okay, so this chart is quite similar to what we studied in the Moody's chart. Okay. Now let us solve this example here. Engine oil at 40 degrees centigrade flows over 5-meter long flat plate with a free stream velocity of 2 meters per second. Determine the drag force acting on the top side of the plate per unit width. Okay. Now the length of this one is given, the velocity, which is the free stream velocity, is given, and we have to estimate the drag force. Now this system, it is an example for the flat plate, so we will be using this equation. First of all, we will use the equation for the Reynolds number calculation, VL divided by kinematic viscosity. So we will be getting the value for the Reynolds number. Now this value, this lies in the region for the laminar flow. Now for the laminar flow, we have to calculate the value for the coefficient of friction that lies for the laminar flow. Okay, so the equation that I showed you earlier, if we are dealing with if we get the value for the Reynolds number less than this one, then we have to use the equation to estimate the value for coefficient this one. Okay, we will be using this equation again here to get the value for the coefficient of friction for the entire surface, and the value that we get here, it is 0.00662. Now the drag force calculation only be a function of coefficient of friction forces, and A represent you the contact area. Okay, so what is an area? 5 represent you the length of the flat plate, and 1 meter square, 1 represent you the width of the flat plate. Okay, so we have to put the value for the area here. The density is given, the velocity, it is given to you. So the value for the drag force that you can estimate in this problem, it comes out to be 58 Newton. Okay, so this is how we can actually calculate the drag force for the flat plates. Okay, so the important thing is here how you calculate the value for the Reynolds number, and then which equation you can use to estimate the value for coefficient of the drag force. Either it is a coefficient of friction or it is a coefficient of the pressure. Okay, so for the flat plates, what we know, we have to only deal with the coefficient of friction. Okay, so this is all for today. Thank you. Now let us calculate the drag coefficient for the cylinders and the spheres, and which graph we can actually use. Okay, so this is a graph that we can actually use to estimate the drag coefficient for the cylinders and for the spheres. Now for flow over cylinder or sphere, both the friction drag and the pressure drag can be significant. Now the cylinder and sphere, they can be called as a blunt bodies. Okay, now the cylinder and the sphere, they can have both the values for the drag force due to the friction forces and the drag force due to the pressure forces. Now let's see what we have here. The high pressure in the vicinity of the stagnation point and the low pressure on the opposite side in the wake produce a net force on the body in the direction of flow. Now here he is explaining the concept of the drag force due to the pressure drag. So if I take you back here, here we were dealing with this can be taken as a sphere, and also it can be considered as a cylinder. Now at this point where the fluid it is coming into direct contact with this body here, at this point the velocity of the fluid it will become zero. Okay, and there will be a point called as the stagnation point, or the pressure at this region will be called as the stagnation pressure region. Okay, now on the right hand side of the body, what we see here, the boundary layer separation at these 2 points of the figure, and there will be a formation of low pressure zone area behind this object. So this region is called as the wake region. Now for these kind of objects, we can have the drag force due to the friction drag, as more of the fluid is coming into contact on the surface of this body, and also there will be a drag force due to the pressure drag. So we have to consider both the drag forces in these kinds of geometries that lies for the sphere or for the cylinder. Okay, so what we see here, this green solid line, it is the smooth cylinder, and this dotted line it represents you the smooth sphere. So what you have to do in the while calculating the value for the drag coefficient, you have to calculate the value for the Reynolds number, and you have to use this graph. Then you can match the Reynolds number and get the value for the drag coefficient. The drag force is primarily due to the friction drag at low Reynolds numbers and due to the pressure drag at high Reynolds numbers. So at a value for the very low Reynolds number, what happens? There will be no motion of the fluid, and all the fluid will be attached to the surface of the body. Okay, so if the velocity of the fluid will be very slow, and you put a cylinder in that in the passage of the flow, what would happen? At a very low value for the velocities, all the fluid will be covered, all the fluid will cover the entire surface of the object. Okay, so in that kind of case, the drag force will be due to the friction drag. Okay, but as we increase the velocity of the fluid, or we increase the Reynolds number of the fluid, what would happen? The drag force that would be acting on that particular object will be due to the pressure drag. Okay, so when you change the Reynolds number, there will be a change in the drag forces, and you have to see the relevant graph to get the value for the drag coefficients. Okay, now here we have to see a concept of the surface roughness and how the surface roughness can delay a boundary layer separation. Okay, so here I will show you one example. Now let us see one example here for the smooth ball and for the golf ball. And now here we have to see the concept of the boundary layer separation and how we can actually delay the boundary layer separation. For example, we throw this ball, which is a smooth ball, and due to the motion of the fluid over this ball, what would happen? The boundary layer separation occur at this point and at this point. So there will be a large portion of the low pressure zone area behind this object, and there will be large delta P across this ball. Okay, so the drag force that would be acting on this ball will be due to the pressure drag, right? Also there will be some drag force due to the friction drag, but the main factor that will influence the motion of this ball will be the pressure drag. Now let us consider an example for the golf ball. Now if you consider the golf ball and see the structure of this golf ball, you will see small pitches on this golf ball. Now what is the use of these holes or the pitches on this golf ball? That when this ball will be moving through the fluid, what would happen? There will be a turbulence across this ball. Okay, and due to this turbulence sucks air to the ball, separation is delayed. Okay, so when there is pits or this hose on the surface of this golf ball, what would happen? The turbulence around these pitches and the hose, it will increase, and due to the increment in the turbulence around this ball, what would happen? There will be a delay in the boundary layer separation, and when there is a delay in the boundary layer separation, there will be a there will be a less area of the low pressure zone behind this object. Now in this case, due to the geometry of this particular ball, due to the pitches of this one, the boundary layer separation will occur, and now this ball will have the less drag force compared to the ball that we have here. Okay, that is why we keep these pitches and the holes on the golf ball to delay the boundary layer separation. Now we have to see the same concept here. Surface roughness in general increases the drag coefficient in the turbulent flow. Okay, so if we are dealing with the surface with the objects that have the high surface roughness, what would happen? The drag coefficient will increase in the turbulent flow. Okay, so if you are dealing with the turbulent flow, then the surface roughness will increase. Now this is the case for the streamlined bodies. Now for the blunt bodies, what would happen? For the blunt bodies such as circular, a cylinder or sphere, where however an increase in the surface area may increase or decrease the drag coefficient depending on the Reynolds number. Now here we have to consider the example for the golf ball. Now this green line, it represents you the smooth ball. Okay, so relative roughness is 0 here. Okay, but here if the ball is having the maximum surface roughness, if it is having less surface roughness, and as we are moving on the right hand side, what you see here, the surface roughness is decreasing. Okay, so the values are written here. So if you are having the high value for the surface roughness, what would happen when you hit the golf ball? Due to the surface roughness of the golf ball, there will be a delay in the boundary layer separation. So whenever there is a delay in the boundary layer separation, the drag force or the drag coefficient will be heavily decreased. Okay, so at the very low value for the Reynolds number, when you hit the ball, the drag coefficient or the drag force due to the pressure drag, it will be highly reduced. Okay, but as we are decreasing the relative roughness, what is happening? There will be an increase in the drag coefficient. Okay, now this is the part for when you are dealing with the low values for the Reynolds number. But when the value for the Reynolds number is high, what would happen? Now the same curves ending up here. Okay, so at the high value for the Reynolds number, after this region, the ball that is having the high value for the surface roughness, it will show you the higher value for the drag coefficient, and the value for the drag coefficient will be lower if the surface roughness is low. Like in this case here, we are dealing with a smooth ball, so the drag coefficient will be very much low at this point. Okay, so for these kinds of bodies, we can have an increment and the decrease in the drag coefficient depending on the Reynolds number. Okay, so sometimes at very low value for the Reynolds number, we can delay the boundary layer separation and we can decrease the drag coefficient. But at a very high value for the Reynolds number, the drag coefficient will become a function of surface roughness, and if the surface roughness is high, there will be a high value for the drag coefficient. Now let us see this one. Surface roughness may increase or decrease the drag coefficient of the spherical object depending on the value for the Reynolds number. Okay. Now, as I explained you earlier, the drag coefficient, it depends on the surface roughness and the value for the Reynolds number. So for the smooth surfaces, you can have the value for the Reynolds number. You can have the value 0.5 here for this one, and for the rough surfaces, we can have the less value for the for this Reynolds number. Okay, for this drag coefficient. Okay, so if we make the body more rough, we can actually have the less value for the drag coefficient, but at the values higher than the critical Reynolds number, what we see that when we have the high value for the surface roughness, we can have the high value for the drag coefficient. In this equation, CD, that is equal to Ft divided by rho V square A. So Ft represents you the drag force, density of the fluid, V is the free stream velocity or the velocity of the fluid, A represents you the frontal area. So if you are dealing with the frontal area, if you are dealing with the cylinder, the frontal area will be L into D, and if you are dealing with a sphere, then the frontal area will be equal to pi d square by 4. So you have to use these areas depending on the type of object that you are using. Okay. Now this for the golf ball are intentionally referred to induce turbulence at low Reynolds numbers to take the advantage of sharp drop in the drag coefficient on the onset of the turbulence in the boundary layer. The occurrence of the turbulent flow at this Reynolds number reduces the drag coefficient of the golf ball by about half for a given hit this. Okay, so here is the explanation for the golf ball again. Okay, so at the low value for the Reynolds number, what we need to have, the less value for the drag coefficient, or we should have a less value for the drag force due to the pressure drag. Okay, so at low value for the Reynolds number, when we make the pitches or holes on the golf ball, what would happen? There will be a certain decrease in the drag coefficient and the drag force also. Okay, so that is what our requirement is. On the other hand, for example, we take an example for the tennis ball. Now for the tennis ball, what we need to have here, we have the small table and we want to keep that ball on the table. Okay, so when we make a hit, we don't want that the tennis ball will go out of the table. So what we need to have here, we need to increase the drag force, or we have to increase the value for the drag coefficient. Now how we can actually increase the value for the drag coefficient? Again, this figure. Now this is an example for this table tennis ball. Why if you look at the surface of the table tennis ball, it is very smooth. Okay, why we make the surface of this table tennis ball very smooth? So that the boundary layer separation occurs very quickly. So when the boundary layer separation occurs very quickly, there will be a large area behind this object with the low pressure zone area, and there will be large delta P across the body, and there will be an increase in the value for the drag coefficient. Okay, so by achieving the characteristics, we can either induce the boundary layer separation quickly, or we can actually delay the boundary layer separation quickly. Okay, so for the golf ball, we want to have the longer distance, so we can delay the boundary layer separation. For the table tennis ball, we don't want we don't want that the ball will go out of the table, so we induce the boundary layer separation quickly. Okay, so these two things are opposite, but it depends on our requirement. Okay, either we need to increase or decrease the boundary layer separation. Now let us do this example, which is the last one of this chapter. A 2.2 centimeter outer diameter pipe is to span across a river at 30-meter wide section while being completely immersed in water. The average flow velocity of water is 4 meters per second and the water temperature is 15 degrees. You determine the drag force exerted on the pipe by the river. Okay, so we are provided with the outer diameter of this pipeline, and we are provided with the length of this pipeline. Okay, and we are provided with the velocity of the fluid, and we are supposed to calculate the drag force. Okay, now this kind of pipeline, it is an example for the how you can relate this pipeline. You can relate this pipeline with the cylinder. Okay, so what we are gonna do here, we are gonna use the information for the smooth cylinder, and we will estimate the value for the drag coefficient. Let's see what we have here. So first of all, we will calculate the value for the Reynolds number, rho ud divided by mu. Density for the water is given, velocity we know, d is the diameter that is given to you in the question, and mu is the viscosity. So the value for the Reynolds number, it comes out to be this one. Now we are using the case for the smooth cylinders. So at this value for the Reynolds number, we will try to estimate the value for the drag coefficient. Okay, 7.7 multiplied by 10 raised to power 4 here. So if you go back to this graph here, so 7 multiplied by 10 raised to power 4. So this one 0, 2, 4, 6, 7. Okay, so it lies somewhere here. Okay, so this is the point where you will be getting the value for the drag coefficient. That comes out to be 1 for this particular example. Okay, now the drag coefficient here we estimated it to be 1.0. Now here for the calculation of the cross-sectional area, we need to consider what is the frontal area of the cylinder or the pipeline that is coming into contact of the fluid. Okay, so how you can estimate the value for the frontal area? We are provided with the length of this one, and we are provided with the outer diameter of this pipeline. So we can multiply the length with the diameter here, as we know from this one, L multiplied by D here. So we will be getting the frontal area of the object. Okay, so here we will be getting multiplies 30 by 0.022. That will give you the frontal area. The value for the CD we have estimated earlier. Density we know, velocity is given. So you can solve this equation here, and the value for the drag force, it comes out to be 5300. Okay, so we'll be getting this value for the drag force, and this is all for today. And you can go through this example, and if you don't understand anything, let me know. Send me an email or you can contact me. Okay, so thank you everyone. With this example we finish our chapter number 11. Next time we will start the chapter number 9 and see that how it goes. Okay, so everybody, I hope that everybody has enjoyed the lectures, and let me know if you feel any difficulty. Thank you.